Hello, welcome to the first part of my video series on RISC processor pipelining. I want to acknowledge that some of the slides in this deck are derived from the book Slides from Patterson and Hennessy's Computer Organization and Design, and from the slide deck produced by Mary Jane Irwin. Here we see a diagram of a single cycle MIPS RISC processor. If you're not familiar with the design of this processor, you should check out some other videos to help you understand what is going on here. In the single cycle design, the cycle time is set to accommodate the longest instruction, which in the MIPS processor we just looked at is the load instruction. Since the cycle time has to be long enough for the load instruction to complete, it is too long for the store instruction, so the last part of the cycle is wasted. And we can see this shown in the diagram, where in cycle 2 there's a store word instruction, and the end of the store word instruction is doing nothing until the clock tick. This may be wasteful of area, since some functional units may be duplicated, or they can't be shared during a clock cycle. The single cycle design is relatively simple, but nobody actually uses it in practice. So take a look at this table of instruction critical paths to see how we can derive what should be the cycle time. And in the single cycle MIPS design we just saw, we support the R-type instructions, add, subtract, or, and, set less than, branch instructions, jump instructions, branch equal instructions, jump instructions, and the load and store instructions. So we can look at the major components of the processor to determine in what order those components are used by each of the instructions and how long the instruction should take based on some assumptions about the delays for smaller logic gates and for wires, and given these costs of the major components, so 200 picosecond access time for instruction and data memory, 200 picoseconds for the ALU and any adder unit to finish its operation, and 100 picoseconds each for register read and register write. So an R-type instruction accesses the instruction memory, reads from the register file, does some ALU operation, it does not access data memory, and then it writes to the register file. So the total time under these assumptions that an R-type instruction takes to complete through the processor is 600 picoseconds. And so forth, we can calculate that the load, which uses all of those functional units, requires 800 picoseconds and is the longest. Therefore, our cycle time on this processor would have to be a minimum of 800 picoseconds in order to ensure that the load instruction can finish its operation in time. 800 picoseconds is 0.8 nanoseconds, so 8/10 of a nanosecond. So if your cycle time is 8/10 of a nanosecond, you can invert that and you can find out that the frequency would be 10/8 gigahertz. Okay, so looking at a little diagram, a timeline here, we see how if we have 3 load word instructions in a row, each of them would take 800 picoseconds, and on this timeline we would see different phases of the instruction accessing different pieces of the functional unit in each portion of time. One way to improve the efficiency of this sequential process is to separate the resources and overlap them in time in a pipeline. So here's an example that's been used many times before, which is washing clothes. You could wait to finish putting clothes away before you start putting new clothes into the wash, but it is much more efficient for you to start the wash when you move a load into the dryer. We can measure how much better it is by calculating speed up, which we've talked about in a different discussion. Speed up is a unitless measure of improvement to throughput that's calculated by dividing an original time by an improved time. So in this example, we have 4 stages of a resource used with identical latency of half an hour. So the time to complete n loads of wash is 4 times n using the sequential approach, but it's only n plus 3 with pipelining. The plus 3 with pipelining, by the way, is to fill up the pipeline, as you can see in the hours between 6 and 6:30. Once you fill up the pipeline, if you keep it full, then you can complete a new unit of work every single, in this example, every half an hour, in general, every unit of time that, or rather every latency of the pipeline stages. So under an ideal scenario, the speed up of this pipeline will be 4n divided by n plus 3, and that's assuming that you can kind of extend off n into infinity, as it were. And so this idealized speed up is approximately 4. As n grows toward infinity, this would go toward 4. So back to our single cycle MIPS processor design. To pipeline instructions, we have to identify the stages of their execution and divide them up into roughly even chunks of time that we can split the instruction cycle into. So one way we can divide this pipeline into stages is to separate those major components that we were just talking about that contribute to the critical path and place each major component in a stage. Then we'll just sort the rest of the logic between stages. So first, we will put the instruction memory in a stage and call that stage instruction fetch, or IF. Sometimes this will be just denoted F for fetch. Then we put the register read in a stage along with the control logic called instruction decode, or just decode, or D. Sometimes this may be separated out into a decode stage and a read operands stage, and we'll revisit that later when we talk about more advanced pipeline designs. We'll put the ALU into a stage called execute, and we've also got in execute the branch calculations and the branch target and jump target calculations. Actually, we're in decode. Then the data memory access is in the memory stage, mem. And then finally, the register write is in the write back stage. And you'll notice that the write back stage actually also includes the register file logically. We also place some components in parallel to those major components, but those accesses are overlapped with the major components access, which dominates the critical path of each of these stages. So here we can see that each of the 5 steps of the instruction will now take 1 clock cycle to complete. So we're going to shorten our clock cycle, and a clock cycle will now be the time it takes to get through the longest stage in the pipeline. So this will depend on the longest functional unit time. So in the instruction fetch, we'll have accessing the instruction memory and updating the program counter. In the decode stage, we'll read from the register file and decode the operand and the instruction and the control logic. The execute stage will do the ALU, or branch target address calculation. The branch target address calculation is in parallel to the ALU and dominated by it. The branch also has to wait for the ALU to complete the subtraction operation for branch equal to determine if the 2 numbers are identical. The mem stage reads or writes memory, and the write back stage writes to the register file. So if we look again at our sequential timeline in the top half of this diagram, we can see that the pipelined time diagram on the bottom allows us to overlap the different stages of the instruction. In order to do that, we have to make every stage the same length. So now we're adding some holes here because we had 100 picoseconds for register read and 100 picoseconds for register write. So now register reading is going to happen in the second half of the processor cycle, and register writing happens in the first half of the processor cycle time. We'll come back and visit that again later, but the important piece here is that we won't need to be reading and writing the register file at the same time. So the register writes happen on the falling clock cycle, and the register reads will happen on the rising clock cycle, or the register, the high side of the clock cycle, high level. So in a pipeline processor, the basic idea is that we start the next instruction in the program before the current one has completed. And this allows us to increase the amount of work that we get done over a given amount of time by making more use of our functional units that were otherwise sitting idle waiting for the rest of the processor to finish. We may increase the instruction latency, which is the time from when we first start fetching the instruction until it completes. And the reason for that is here. When we expand out each instruction stage, each stage to the same length, we have to increase some of them. So we're going to be adding some waste into each stage. So remember, the register read and register write, they take 100 picoseconds, but we actually expand out those stages to 200 picoseconds. So in the single cycle design, we had wasted execution time at the end of an instruction. Now we're going to have a little bit of wasted execution time within each instruction, within, for example, the decode and write back stages. But overall, we're going to have a much more effective and performant pipeline. So if the clock cycle time is 200 picoseconds in the pipeline design and 800 picoseconds in the single cycle design, one instruction in the pipeline case takes 1,000 picoseconds because it's 5 stages at 200 picoseconds each. So the latency of this instruction is longer by 200 picoseconds, or approximately 25% longer in the pipelined case. However, the throughput is much greater. So 1,000,000 adds in the single cycle design takes 1,000,000 times 800 picoseconds. So that's 800 million picoseconds, which is 800,000 nanoseconds. So it's 800 microseconds. 1,000,000 adds in the pipelined case takes 800 picoseconds to fill up the pipeline. So the first 4 instructions into the pipeline, remember we talked about n+3, right, as the time it takes a pipeline with 4 stages. Well, this pipeline has 5 stages, so it's going to take n+4 times to complete n instructions. So we've got those 1,000,000 adds, and so we're going to have n, which is 1,000,000, plus 4 instructions. So now each stage takes 200 picoseconds. So it's n plus 4 multiplied by 200. So it's 1,000,000 times 200 plus 4 times 200. So that's 200 million plus 800 picoseconds. Okay, so that's about 200 microseconds and change versus 800 microseconds. So our pipeline design is much more effective. It really gets the job done quicker. So we're going to represent the pipeline in a few different ways, and here's one graphical representation of our 5-stage MIPS pipeline. So we've got our instruction memory, our register access, our ALU access, our data memory, and our register write. So our fetch, decode, execute, memory, and write back stages, shown here as a sort of a very simplified structural diagram of the pipeline. We could construct different kinds of pipeline structures. So if you had a slow multiply operation, you could make the clock cycle time twice as long, or you could let that multiply operation span multiple stages. So for example, the multiply operation might go in parallel and overlap with the regular ALU and data memory accesses, so that a multiply instruction takes 2 cycles, or rather consumes those 2 cycles that would normally be used by the ALU and the data memory, under the assumption that it doesn't use any of the components in those 2 paths. And then if the data memory access is slow, you can divide the data memory access into multiple stages. So you can make the data memory access take multiple clock cycles in order to keep your clock at the same rate or to increase its speed. And we'll hopefully be able to review some of the pros and cons of these designs at another time. So as an examples, the ARM7 processor is, or the ARM processor is a very simple 3-stage pipeline. It just does an instruction memory access, a fetch stage, which does the IM, and a reg stage, read operand stage, which does the decode and the register operand accesses. And then the execute stage does everything, the ALU operation, data memory access, and writing back the result to the register file. Other kinds of pipelines may divide the instruction memory access into multiple cycles. So the X-scale processor here is shown with 7 stages. And so the instruction memory access here takes 2 stages. In the first stage, the program counter is read from, and you begin the instruction memory access, and you also query the branch prediction structures to decide if you should try to do a branch prediction. IM2 finishes the instruction memory access. The reg stage does the reading of the register operands and decoding the logic. There's a shifter stage, which begins a shift operation followed by the ALU stage, and then the data memory access stage is split into 2 cycles, with the second cycle of the DM2 overlapping with the register write operation. So we pipeline in order to improve performance of our processor. So we've got our 5-stage graphical pipeline here. And ideally, we would see something like this, where as each stage completes, we can begin the next instruction. And so instruction 0, when instruction 0 is in the ALU stage, instruction 1 is in the reg stage, and we're starting the instruction memory fetch of instruction 2. Our ideal case is when the pipeline is full. So our time to fill the pipeline there, that's part of our pipeline overhead. That's our +4 in our idealized speed up equation. When the pipeline is full, 1 instruction will be completed every cycle, right? So here in this first pipeline full cycle, instruction 0 finishes. In the next cycle, instruction 1 is going to finish, and as long as the pipeline is staying full, instruction 5 will begin. And so then instruction 2 will finish while we fetch instruction 6, and so forth. And as each cycle completes, 1 instruction finishes. In order to make this work, we have to separate the stages in order to time them properly. So in order to align their timing to each other. So what we introduce are these state registers. They're called interstage buffers or pipeline buffers. And they're registers. They update their value at the end of the clock cycle, so on the falling edge. And they latch the value of the output of the stage in order for it to be consumed by the next stage in the next cycle. This way, it doesn't matter how quickly any particular path through a stage goes. all paths end up being synchronized at these interstage buffers. So the clock is wired to all of those buffers, and actually getting that clock to tick at the exact same time gets a little bit complicated as circuits get larger and larger, but by and large we'll ignore that factor. So all the control signals are determined in the decode stage by the control logic, and then they pass down the pipeline through the interstage buffers. So the control logic also gets added in these pipeline buffers, and as each control signal is read or used, rather consumed in a given stage, then we don't have to buffer that signal any further down the pipeline. So that by the end of the pipeline, the only signals we're left with are the ones that we need in the final stage, the mem write-back stage. And we indicate these buffers by the names of the two stages on either side of them. So we'll call the IFID interstage buffer between the IF stage and the ID stage. So the control logic, we've talked about this before. Control logic, as we go down the pipeline in the execute stage, will have 4 signals that get consumed: the regdest, ALU op1, ALU op0, and ALU source. And then in the mem stage, we've got these 3 signals that get consumed: the branch, the memory, the memwrite. And then in the final stage, we've got 2 signals left. So now we're going to look at another way of representing the pipeline operation. Well, we're going to look at 2 ways of doing it. One is going to be a very detailed look that looks at the entire slice of the pipeline in order to see how resources are used. And then the other is a multi-clock cycle diagram, which is going to be a very sort of is a general tool to help understand how the pipeline operates. So here we're going to look at our single cycle slice, and we're going to look at how a load word goes through the pipeline. So in the instruction fetch stage, the load word accesses the instruction memory, and it adds the PC+4, and it's going to write into the IFID stage, interstage buffers. Then when it advances to the next stage, it's going to have whatever the bits came out of the IF stage will be read from and passed into the register file. The control logic is not shown here, and the immediate is signed and extended, and those values are written into the interstage buffer into execute. In the execute stage, the effective address gets calculated. In the memory stage, the load actually happens, and then in the write back stage, we're going to write the value back. But if we just took the write register index that was produced or that was in our original single cycle design without taking into consideration the pipelining, then we would actually be writing into the write register specified by whatever instruction is 3 cycles after the load word. So what we have to do is we have to pass our write register index through the interstage buffers as well, so that when we get to the write back stage, we provide the write register index and the write data and the write signal, the reg-write signal, to the register file at the same time for the correct instruction. Store word is very similar in the first 3 cycles. So we calculate the effective address. Then in the memory access, we're going to actually write to the register file. And then in the write back stage, there's nothing to do, right? We just do nothing. So the store word is done. This is that wasted part of a single cycle design. But in this design, while we're wasting this part of the processor time, the rest of the processor is actually being used processing stages of 4 other instructions. So now we're going to turn this into a multi-cycle pipeline diagram. This is a very useful tool. So we're going to have the clock cycles along the top increasing, and we're going to have the instructions of the program in the order that they're executed along the side there. So in a sequential piece of code, we'll just have the instructions PC plus 4, PC plus 4, PC plus 4, and so forth. When there's a branch or a jump, then we may have to go to a different place in the program in order to get a different instruction. So you can see the little snippet of code here is doing a load, a subtract, an add, a load, an add. The actual instructions don't really matter all that much. And we can see how the stages are sort of laid out in time. So instruction fetch, decode, execute, memory, and write back. And we can actually we'll simplify this even further to the letters of the stages, I, F, I, D, E, X, M, E, M, W, B. Or we may just simplify it to a single letter. F, D, X is often used for execute, M for memory, and W for write back. So here we have our pipeline is full, and this is our ideal case. Our single cycle pipeline diagram for that slice would look like this. We would see all of these 5 instructions in each of these different stages of the pipeline. So our write back stage would be writing back our first instruction in the sequence, the load word instruction, while the sub instructions in the memory stage doing nothing. The add instruction is in the ALU or execute stage, computing the addition. The load word is in the decode stage, getting its register operands, and the instruction fetch stage is fetching the 5th instruction in the sequence, another add instruction. So pipelining is great. There are some problems with it. So one problem is handling instructions after a branch. So the branch instruction is calculated at the, we're currently calculating it in the mem stage. We finish it, and in the mem stage we update the program counter. So the instructions after the branch, that add I instruction, if the branch is taken, we wouldn't want to execute that add I instruction, because in the sequential flow of the program, we expect that if a branch happens and you follow that branch, then you don't execute the instructions that follow that branch. So we have to make sure that that happens in our processor design. So instructions after a branch can be a problem. Same with instructions after a jump. And then it can also be a big problem if we need to read from a register after it's been written to. So this is called a read after write dependency. It's on the bottom here. So we see that we have this load word instruction that's going to load the value from the base register S1 plus the displacement of 12 bytes. And it's going to load that value and write that into the S0 register. Well, it's going to write that value in the write back stage. The add instruction there, S3, S0, S1, is going to be in the mem stage when the load word is writing back its value, which means that it's already going to have calculated its addition of S0 and S1 using an old value, a stale value of S0. So that's not likely going to be the correct value. You certainly can't guarantee it'll be correct. And so that's going to be a problem. And we're going to talk about those problems in our next discussion. So these are called pipeline hazards. They're structural hazards, which try to use the same resource of two different instructions at the same time. Data hazards are that last example where you try to use data before it's actually available. And then control hazards, which are control flow problems where you have to make a decision about the program control flow before the condition has actually been evaluated, and you jump or branch and you have instructions that follow. You can often resolve these hazards by waiting. You can't resolve exceptions by waiting. The pipeline control has to be able to detect the hazard in order to determine that it should wait, and then take some action to resolve the hazard. So pipeline is efficient and effective. It uses more of the hardware more of the time. There's still some waste. Can't get rid of all of it, apparently. But you can work on multiple in-flight instructions simultaneously by overlapping their execution in stages. Pipelining does introduce new problems that we're going to have to resolve. So structural hazards, data hazards, and control hazards. So next time we're going to talk about resolving structural and data hazards.